Welcome. In this video, we'll step through using the Normalcdf function on our graphing calculators to find the area under a normal distribution curve. And for the purposes of my examples today, I'll be working with the standard normal distribution, so that special case of the normal distribution. So when we're looking for area and using Normalcdf, we'll be entering a lower bound and upper bound, defining the region or area we're trying to find, followed by the mean and standard deviation of the normal distribution. So as we'll be dealing with standard normal, the mean is 0 and the standard deviation is 1. And it turns out that standard normal is the default on the graphing calculator. So generally speaking, you would enter those 4 pieces of information. But for standard normal, if you don't enter a mean or a standard deviation here, the calculator will assume you mean this standard normal. So it saves us a little bit of typing. And then as we do our examples, I will be working with stat wizards turned off. So if you did want to check on your calculator, if you go to your mode button with stat wizards, if you have stat wizards, not all calculators do, but if your stat wizards are turned off, then your calculator display will match mine. With stat wizards on, nothing wrong with that. It's just that the interface looks a little bit different, and I will be working with them off to accommodate all calculators. Okay, then we're ready to jump in here. So we're going to go through 3 cases of using Normalcdf. So the first case here, it says find the area under the standard normal curve between z equals negative 1.96 and 1.96. So we'll be using z to represent our values from the standard normal distribution. I'm going to go ahead and label my axis here. So when we're working with z-scores, the mean 0 is in the center. And then we will just estimate there, negative 1.96 is awfully close to negative 2, and 1.96 almost at 2. So that area that we're seeking is the area between those 2 values, or equivalently, we could say, what is the probability of a z-score being between those 2 values? So the area is defined by its lower bound and upper bound. And we're ready to go. So I'm going to abbreviate normal just N. So NCDF, we're going to enter our lower bound and our upper bound. And usually you would have to enter the mean and standard deviation of your distribution. But again, since we're dealing with standard normal, we're able to leave off those values, and the calculator will assume that that is what they are. Okay, so we're going to go to our distributions. So second, distributions. Choice 2 there is your Normalcdf. And then to enter the negative 1.96, just remember to negate a number, you want to use your negation button, not your subtraction button. So negate, and then 1.96, comma 1.96. And I'll be rounding my areas or probabilities to 4 places. So that will be 0.9500. And I'm also going to write that as a percent, 95%. So on this picture, I've shaded the middle 95% of that graph. So the area under the entire graph would be 100%. So it's not 100%, but it's getting up there, 95%. So there is still some area unshaded in these, what we call the tails. But just informally, we often say that values in the middle 95% are somewhat typical. It becomes unusual to get values further away. So throughout the course, we will often see this percentage coming up for that reason, which means that we're going to see that z-score 1.96, negative 1.96 as well. We'll see those values coming up quite a bit moving forward. All right, so that's the first case. So between two z-scores, we'd have to use our normal CDF and those values defining the region as our lower bound and upper bound. So the next question is, what if there is no upper bound? So that's going to be my case 2. So case 2 says, find the area under the standard normal curve to the right of z equals negative 1.28. All right, so for my z-scores, 0 at the center. So negative 1.28, you can just approximate there, negative z-score to the left of center. So the z-score is to the left of center, but we're looking for the area to the right of it. Now, in theory, the graph continues indefinitely. We say without bound. So z-scores can be infinitely large, but the area under the graph does start to get smaller and smaller and smaller the further away from center we go. So they do, though, go on indefinitely. So infinity is that concept of they just continue to grow. So we do have a lower boundary, but we actually don't have an upper boundary. So there is no value where you stop. You can always go further. But the calculator needs a number. So we have to use a number to sort of stand in for the infinity idea. So what we do is we pick a number so big that when we're looking for the area, we'll get the accuracy we desire. So we're going to pick a number very large, and the number we pick is going to be a 1 followed by 99 zeros. So that is a pretty huge number. It's called a duotrigentillion, fancy name there, and we'll just use that as our stand-in for infinity. So on the calculator, to get here's our scientific notation for that number, 1 times 10 to the 99. What we'll do is enter 1, and then the E for the scientific notation, and then the 99 moves the decimal point to the right 99 places. So infinity is not an upper bound, but we'll replace it with that number. So let's give it a try here. So normal CDF, we'll enter our lower bound first. So we're going from negative 1.28. And then for the infinity, I know I wrote there 1E99. It turns out you don't even have to type the 1. So I'll show you just how to get the E99. All right, so let's clear the calculator here. All right, so I'm going to go back to normal CDF and then enter my lower bound, negative 1.28, comma. All right, so to get the E, if you look above your comma button, you're going to see EE, a double E up there. So that's what I want to activate. So I'm going to hit my second button and then my comma button, and you will see a single E appear on your screen. So that's how we get the E. So second comma, and then the 99. So that will be a 1 followed by 99 zeros, and enter. I'll again round to 4 decimal places. So that's 0.99, I'm sorry, 0.8997. 0.8997. And since I wrote the other one as a percent, I'll write this as a percent as well. So 89.97% of that picture is shaded. Okay, one more case. So what if we wanted to know the area to the left of a value? And I'm going to stick with my same z-score. So now z of negative 1.28, but I'd like to know the area to the left of it. So just like the right side, there is no end. We continue indefinitely in theory here to the left. So that idea of negative infinity. So we need to put in a number though, so we can't work with negative infinity. So basically, we just take the negation of the number we used before. So our 1 with 99 zeros was over here, and we'll just use the negative of it, and that will be our stand-in for negative infinity. Now, the thing you really have to be careful of, though, is the order that you're entering values into the calculator. So when we define a region, the lower bound is always to the left of the upper bound. So when we get to our normal CDF and we're looking for the probability of a z-score being less than a value, the starting point is the negative infinity. So we'll do our negative and then the E99. And then the upper bound is the negative 1.28. All right, so just going to come back here for a second. When you're looking for area to the right, you start with the number and then the infinity. So it was the number and then the positive infinity. But when you're shading to the left of a value, you're always starting at the negative infinity as your lower bound, and then your upper bound is your number. So important to get the entry order correct. All right, so let's go to our distributions, normal CDF, and now negate, and then negate your E, second comma button. So that is our E, and then the 99, comma, negative 1.28. And I'll round that to 4 places, 0.1003. And writing that as a percent, that would be 10.03% of that picture. All right, so I did want to just use the negative 1.28 in both cases so that you could see that this area, 89.97%, plus this area, the other 10.03%. So if we put those two areas together, we would get 100%. So those are our 3 cases of how you'll use normal CDF to find area or probability.